Well, thanks to the organizers for the opportunity to come here. It's nice to be back in France. Yeah, so I'm talking about dynamical degree. This is joint work with Jeffrey Diller, Mattias Jonsson, and Holly Krieger. So I wrote this, yeah, and it was a lot of fun. So I'm going to just start with the idea of a map on projective space to projective space. And just in case you don't know, this is given by an d+1 tuple of polynomials. And I'm going to use this notation for points in projective space with the usual equivalence that if I scale by a non-zero number lambda, I get the same point. And in order for this to be a map, I need P0, PD to be homogeneous, meaning that every monomial that occurs with the same degree of some degree m and of course, I don't want them to share any common factor. So there's no q that I can divide out of all of them, right? That's what I need for a map. So there does not exist a non-constant q such that q divides pi for all I. And when I have this situation, then I'm going to say that the degree of phi is equal to m. Okay, so that's the starting point. Okay, hopefully I can get that down at some point, but maybe not. So let me just see an example. So if we start with our map phi, we'd like to look at iterates, so I can iterate the map, and I get a map from PD to PD. And I should say that I'm only assuming my maps are rational, so they don't have to be defined everywhere on PD, on projective space. And I can look at the sequence of degrees of phi to the n. And naively, we might think that if I take my map phi and I compose, well, now I'm just plugging in the polynomials into my map. And if I plug in a bunch of degree m polynomials into a degree m polynomial, I expect to get a degree m squared polynomial. So I can actually get, well, I'd like to say that it's degree m squared, but it's actually in general an inequality, the degree of m squared. And the reason why it's an inequality in general is because even though the p's share no common factor, it's possible that when I perform this composition, I get a common factor that I can cancel out and that drops the degree. So as an example, let's take an example. So here's on P2 to P2. And I'll use coordinates x, y, and z. So I can make the map xz and xy. So this is the famous Noether map. This is what's called a birational map. So it's got basically an inverse. And it's a degree 2 rational map. And in fact, if you look at the birational maps on P2, they're generated by this phi along with the automorphisms, which are PGL2. But let's see what happens when we compose phi with phi. So if I compose phi with phi, so now I'm plugging in, I'm taking this times this to get my first coordinate, so I'm getting x squared yz. And I'm taking this times this to get my second coordinate, so I'm getting xy squared z. And I get this times this to get my third coordinate, so I'm getting xy z squared. And like I said, we eliminate any common factors, so I'm going to get a common factor of x, y, z, and when I divide it out, I see that I just get this map. So this phi squared is actually just 1. And I can see that in general, I'm going to get that the degree of phi to the n is either 1 or 2. So it's 1 if n is odd. No, it's 2 if n is odd. And 2 if n is odd. And what I can think is that dynamically, this sequence is telling me that this map is fairly tame, right? It's just an involution on projective space. So in general, what we have is that degree of phi to the n plus m right? This is just the submultiplicativity. Like we said naively, we'd expect to get an equality, but because we can have cancellation, it can drop. So that's the degree formula. And what that means is that we can associate a quantity called this limit and submultiplicativity will give me that this limit exists. And this is some number. And because the degree is always bigger than or equal to 1, it has to lie on 1 infinity. And because the degree of phi to the n is less than the degree of phi to the n, it's going to be a finite number. So that's called the first dynamical degree. So we've done it just on projective space, but we can do it on any variety. One way you can think about it is in projective space, I can think about taking a hyperplane and looking at the pullback, and I get some region. And if I want to look at degree, well, if we look at Bezout's theorem, right? Bezout's theorem says if I take a degree d curve in P2, if I intersect it with a line, I'm going to get 2 points, counted with multiplicity. So I can think about taking a degree function on projective space. If I want to associate a degree to my map, I can take some generic hyperplane, pull it back n times, and then drop the degree to 0, drop the dimension to 0 by intersecting with d minus 1 generic hyperplanes. And that will give me a finite set of points, and I can use that as the degree. That allows me to extend the notion of degree to any variety. The one little subtlety is that degree isn't really intrinsic once you go outside of projective space, right? I don't have a notion of degree without having some reference to projective space. As it turns out, it doesn't matter how you embed into projective space as far as this dynamical degree is concerned. So it's independent of choice of embedding. So we can do this for any x, phi, and phi here is a rational map from x to x. Okay. Any questions so far? Maybe not. But if there are, I don't know. Let me look at a few more examples. It'll be easier for me to just work with affine space to do some examples. So let's do some more examples. And I'm going to work on the affine plane, and I'm going to take a map from A2 to A2. And this is a very nice map. And we can see that if we compose, what do we get? We get x and I can see, I mean, I'd have to make sense of this, but I can see the degree should be n plus 1 in this case. So the degree of f to the n is n plus 1. And if I take the nth root of this, I see the dynamical degree of this f is 1. And on the other hand, let's do another example. So we all probably know this matrix 0, 1, 1, 1. You would teach linear algebra and you do the Fibonacci recurrence, use this matrix, right? So we can make a map out of this by saying xy goes to y, xy. So I'm using the columns and I'm saying x to the 0, y to the 1, x to the 1, y to the 1. And this is a monomial map. And it's a straightforward exercise that if you iterate this map, well, I say it's a straightforward exercise. I don't know what you get here. But basically, you get something with Fibonacci numbers because of the eigenvalues of this matrix. Fibonacci numbers grow like the golden ratio, and we can see that the dynamical degree of this is 1 plus root 5 over 2. And we should think about it with the following idea, is that if we have an algebraic dynamical system, it's a very complicated thing where points are moving around. And this dynamical degree kind of gives us a snapshot of its complexity, right? In the sense that here, the dynamical degree is 1, and we can think of this as a fairly tame dynamical system, right? It's fairly easy to understand. It's just taking x, y, and it's sending it to x, comma, xy, and I can understand where the points are going. This one is a little more complicated, right? I've used up all the boards already. No, I haven't. Let me try doing this. And let me just state some facts. Well, you'll see this is an example of where you get an algebraic integer. So in general, so lambda f is a real algebraic, I guess it would be a real algebraic integer, actually. But lambda f is this if f is what's called algebraically stable. And all this means is that pullback commutes with iteration. So that applies to a large class of things. In particular, it applies to birational maps of surfaces. You can arrange it in this sense. And what you can do is, I guess I should say that here x is projective, and we've got f as a map from x to x. And algebraically stable will basically mean that if you look at something called the Néron-Severi group, you can compute it from just spectral radius here. Okay. Like I said, Diller and Favre. And I think Favre is one of the organizers or something of this. Maybe? No. But he's something. And he's related to this some way, right? Okay. He proved that it's true for Burr P2. So anything built up from this Noether map, but also things in PGL2 and compositions of these, you can obtain algebraic stability. So Favre and Jonsson, Mattias, they showed that for maps of A2, you always get a quadratic integer. So things like this, which fits with this sort of thing. So we get quadratic integer. And Bonifant, Fornès, and Jurek showed, not together, showed that there's only countably many distinct algebraic dynamical degrees, right? So as you range over all possible varieties and all possible maps and also all possible base fields, no matter how big, you'll still only get a countable set of things. So all of this led to the suspicion that the dynamical degree should always be an algebraic number. So so the original motivating question, I was really sort of right time, place, right time to do this. So it wasn't something on my radar. But the original question was, is lambda f always an algebraic integer? And the answer is no. So I'll say that first, with Diller and Jonsson, we found a map f not birational, obviously. And then in a somewhat harder follow-up with Holly Krieger, we found a birational map of P3. And this is a lot more involved and somewhat more interesting because in general, you expect most maps to be kind of birational, right? It's actually an unusual thing for a variety to have non-dominant maps, self-maps that don't end up being birational. Oh, now I should get this down. Let's see how this works. No? Okay. Let's actually do, oh, no. I was trying to do too much. Can I do this though? All right. I didn't do it hard enough. Okay. So it does not belong to Q bar. Where's the eraser? That's what oh, here it is, okay. So any questions so far is okay? So my plan is to first talk about this, which is a little easier to understand, talk about extending it to here, where the same ideas work. So I should say I didn't come up with these maps. So the map is really built up from two things. So I'm going to take a map of the form tau composed with sigma. So what I'm doing is I'm fixing a copy of C star squared in here. And then if I use coordinates y1, y2 here, I can see my map this way. And then sigma is a map of this form. And we need some constraints here. So we need that if we take a plus ib, well, we can write this as root a squared plus b squared e to the I theta. Maybe I'll make it 2 pi I theta. And we want that the theta is not a rational number. Okay? So those are the constraints we're needing. And this map, sigma, is a birational map of order 2, like the Nash map. And then the theorem is that lambda f is not in Q bar. So as long, oh, yeah, no? Okay, as long as this theta is irrational, right? So we need to have an irrational multiple of pi is our argument. So we don't want any power of this to be a real number. Okay, so now, and then probably I can pull this one down, maybe, but that's the one I just used, maybe. So maybe I want to pull this one down. Okay. Oops, I'm on the wrong spot. Well, to approach this, we need to understand the degrees of f to the n, and we're going to call these numbers e sub n. And we want to understand how these nth roots of e to the n are growing to get this transcendence. Of course, it's very hard to understand this in the abstract, So what we want to do is we want to relate it to the map tau, which is dynamically a little easier to understand. So tau, we're going to let their degrees be dn. And dn, I should note, is kind of easier to understand. So we know that if we let d of x be the generating series, because this tau is a monomial map, it's fairly easy to compute. We know that the dynamical degree of tau is just this algebraic number. So what we find is that we have the following recurrence. If we want to relate the degrees of f to the degrees of tau, we've got that En satisfies this recurrence. And to do that, we need to do something a little awkward, which is to define the zeroth degree of f to the 0 to be 2, and the degree of tau to the 0 to be 1. Other than that, we just take the usual degree definition. And we have this, which tells us that at the level of generating series, that we have so we've got this relation. And this relation is going to tell us something, because what we know is that the dynamical degree of D is bigger than the dynamical degree of E. And so what happens is we also know that that as we approach the dynamical degree, if I got this right, I guess I want 1 over this, perhaps, right? 1 over tau. So I know that that 1 over the dynamical degree is the radius of convergence, and as I approach that from the left, I know that it diverges. Okay, that's just an exercise. And what that means is that there's going to be some point where you hit the number 1. Now, why is that not 0? Maybe I need a 2 minus. Oh, no, sorry. This should be n bigger than or equal to 1. And this is n bigger than or equal to 0. So what we know is that there exists some point alpha in 1, whatever this is, where this d hits 1. And that is going to be needed to be offset by this having a pole. So that is the radius of convergence of this. So we can understand lambda of our map F. Well, that's the radius of convergence of this E, and that's going to be hit at this point 1 over alpha. So notice that we've translated the question now as a question of proving this number is transcendental, where it is the number where d of alpha is 1, right? Okay, so this now ties in with Boris's talk from earlier today. I have a feeling I'm going to misspell this. Shidlovsky. Is there a 2 I's in Shidlovsky? It's like, is it? Okay, thanks. Boris mentioned this. The general philosophy behind Siegel-Shidlovsky is you start with a power series. Let's say it starts with an E function, but let's just talk about it generally as just some power series that converges in some radius of convergence. And we've taken point alpha in Q bar. And we'd like to say that when we plug in the alpha, into h, we get something that's transcendental. And of course, there's one obvious obstacle for this working, which would be if h of z was itself an algebraic function, in which case every point I plug in is going to be algebraic. So of course we want h of z transcendental. Of course, even then we could cook up examples that are transcendental, but you plug in any point in the radius of convergence, you get something rational just by making some weird function. So we wanted to have some nice structure. And so Siegel-Shidlovsky was originally being an E function, but then Philippon and Boris, Adamczewski, and Colin Favre-Jean extended it to M functions. But we have some additional structure. And with that additional structure, we hope that if you plug in an algebraic number in the radius of convergence, you get something transcendental. Of course, even that's not quite true because there might be some bad counterexamples, right? Like with e to the z, we plug in 0 and we get something algebraic. But outside of some bad set of examples, we should have this, is the hope. And how's the approach? Well, the approach is you take your h of z and you use the structure to produce nice rational approximations to your function. And then the idea is that, and maybe I'll write it in the sense of this. Let's say that it's h of z is some rational function of degree n plus some error term so that it's small. And then what we hope is that h of alpha should be very close to this. And then the idea is, right, if you get an approximation that's close enough, then you expect it to be transcendental, right? That's the philosophy. Of course, what could happen is we could have a bad point where this is actually exact, in which case, okay, then it's a bad point. But that's the general philosophy, right? It's used. Now, as Boris mentioned, it's not really just the naive Euclidean place that we want to use to measure closeness of approximation. We want to use all the p-adic values as well. And that's something that's captured with Schmidt's subspace theorem. And that was used by Corvai and Zanier in this way, and then famously by Boris and Jan, who did the transcendence of irrational automatic real numbers with this subspace method. So we're going to talk about this. If I can find my sheet. Okay. So how do we do this? And what time do I go to? I guess I go to 5 minutes before or something. Okay. It's confusing to me, but I can figure that out. Okay. So why this is actually very useful to us is because this map tau is a monomial map. It's quite easy to compute the degree. What happens is you compute it on some projective model. You get some cancellation, but it really depends on this angle theta. So what you've got is you've got this angle theta, which I guess is still up there. And if I look, what we do is we divide the unit circle into a bunch of regions. I don't remember, maybe 8 regions. Okay, let's. And how it works is if I want to compute the degree of lambda to the n, then it's a bit like the Sturmian sequences, if you've seen these before, right? You look at where e to the 2 pi I n theta lands, and it lands in one of these regions. So here we're on region 5. And I have a rule for computing the degree if I land in this region. So I have a separate rule for each region. So degree if in region K, use rule K to compute So I won't say too much about what these rules are. They're not too difficult, but they're not too informative either. But the important point is that if I just picked one rule and just used this always, I would get a rational function. Okay, so the rules are kind of nice. Okay? So let's see. I guess I'll bring this one down. And I should do this one a little harder than last time, but not too hard. Oh, it's pretty good. I can't do that, repeat it though, I don't think so. I just won't try. So what's the idea? If I have my function d of x, well, we all know this fact that theta is not rational. And what that means is that I can find some multiple of it that's very close to 1, right? So there exist n such that e to the 2 pi I n is 1 plus maybe something like this, right? So I can get things very close. And what that means is that when I apply my rule, well, if I'm on step k and I'm in this box, so if I want to compute degree of tau to the k, and I'm in this little segment that tells me to use this rule, then almost always when I apply x to the k plus n, when I look at the k plus n, my angle theta stays very close to the angle here. And so I should be applying the same rule. Of course, what could happen is I could have some very bad luck where at some step I'm right on the threshold of applying one rule and the other. And when I look at k plus n, I cross the threshold and I use a different rule. Okay? But that shouldn't happen very often. So what we can say is we get the following fact. So there's an infinite set of n such that we get an approximation of the following form. I should have Z. I can make C as big as I want, so let's just take C bigger than or equal to 10 or something like that. Okay. Now, what is the point of this? So this S doesn't depend on N. If you're wondering where these terms come from, it's exactly this point that sometimes you might be right near a threshold and then go over. And that's reflected in these sort of error terms where we don't get an exact approximation. So we have to go like this. So we get something like this. The n, so S is fixed, and N1 through NS are between N and Cn. Okay. So now what I'll do is I will, sorry. I'm a little disorganized here. Okay, so Boris talked about places today, so I won't have to say anything about this and heights. I might have to say one little thing about heights, but let's see. So I'm going to give a Evertz's theorem, which is more or less just Schmidt subspace, but in a slightly more convenient form for us. So Evertz's theorem says I take the following. So I've got K as a number field, and S is a finite set of places, and it should include all the infinite places. And if you want to think about just the rational case, I'm just saying we need to include the Euclidean absolute value as one of our places. But in general, right, our K can embed into the complex numbers a bunch of different ways, and I have to use all of those corresponding Euclidean values on the space. And let's just fix an embedding into C, and I'll just use the Euclidean space to the Euclidean absolute value to mean this. So now it says the following. It says, so what does this mean? OKS is basically the ring of S integers. So it's the set of points in K that have absolute value 1 outside of V. So if I were to think about it with the rational numbers, and maybe I have the infinite place, and then the 2-adic place and the 3-adic place, then I'm just saying all p-adic values are 1 after I avoid 2 and 3. So it would just say my denominators have to be powers of 2 and powers of 3, right? It would be integers, this. And suppose no subsum So suppose I can't pick out some subset of the indices, some non-empty subset of the indices, such that when I add those, I get 0. So suppose I have this. Then there's a fixed constant C such that if I look at how big this is, it can't be too small. Okay? So you can think about this as being something like an S-unit theorem, saying like if I take a bunch of, 1/2 to the A's and 3 to the B's and try to get something very small, I can't make it too small compared to the heights of these. So this is bigger than or equal to the max of x1 infinity xm infinity. And then I have to do something like this. And I'll explain what I mean by this notation. Can people see around this piano? Actually, maybe I should raise this up a bit. Okay. Huh. Yes? Ah. Yes, thank you. Yeah, yes, you're right. Yeah, thank you. I will, okay, I've got 10 minutes so I can say this. So this is just the S height. So it's like what Boris said, except without the logarithm. And we only look over the places in S to determine size. And basically, this constant C should only depend on my M and my epsilon. And other than that, it doesn't matter. So you can't get too small. And yeah, so I should think of it as saying that if I take a sum of S integers, it shouldn't be too small compared to the size of the S integers themselves. Okay, so now, remember what we've got is we've got a number d alpha is 1. And I should say that these CIs all lie in some fixed finite set. And how the proof is going to go is we're going to assume towards a contradiction that alpha is in Q bar. Well, these CIs are just algebraic numbers themselves. So I'm going to make a huge number field K that contains alpha and all these coefficients. So K. And then what I'm going to do is I'm going to write this. I'm going to plug in alpha into this expression. And what I've got is d of alpha minus alpha to the n. And because of the error term, I know this is very small compared to alpha. Alpha is less than 1, so this is going to 0 very quickly. Now, I'll say what the idea is, and it's the same idea as what Boris and Jan did in their paper. So they want to look at a very specific set of places. So we're going to take S to be all infinite places, along with all places where one of these CIs is not equal to 1, or alpha is not equal to 1. And because these C's lie in a finite set, this is only going to give rise to finitely many places. Now, I'll just say very quickly, because I don't have much time, but what is the point of doing this is that notice that when I look at this contribution, it's not going to give very much, right? Because if I take this to be x1, x2, x3, x4, and so on, and this is s plus 3, then I can see that all of these things are going to this product is just going to give me 1 because of the product formula. So this is just going to contribute 1. And as far as these terms, they're very small, so they don't contribute much to the size. And so really what I get is something kind of small, and something kind of small, but not that small. And on the other hand, I have that it has to be, so this has to be very small because it's less than alpha to the Cn. But on the other hand, this can't be too small. And so that gives me the contradiction. It gives us this contradiction. OK, so that's the idea behind it. Now, the only thing that remains is really we produce this approximation. Well, we have to verify that no subsum vanishes, right, to use the thing. But of course, if some subsum from here vanishes, it's OK. We can just throw it away, and we still have approximation of this form, so it's OK. So the issue is really when we have some subsum involving terms like this. And you can show from very ad hoc methods, so it's not a very nice way, but you can just show by using estimates that you can't get an approximation like this is 0. And then that gives you that it's transcendental. OK, so I have about 4 minutes. Let me say that this was extended, like I said, with Holly Krieger. And this was really a fun project for us. So now we have a birational map. And it's much of the same form, but now it's a little different. So what happens is its F is phi inverse composed with M minus I, composed with phi, composed with MA, where A here is a matrix in SL3Z. And what I mean is that if you give me a matrix Bij that's 3 by 3, I can make the map MB so basically the analog of the monomial map up there, x to the b 1, 3. Okay, I ran out of space. But basically, you get a map of this form. And it's more involved because it's working in a higher dimensional space. I will say, though, what we showed was actually a strange phenomenon. You know this poem that says, like, water, water everywhere and not a drop to drink or something like that? Is that a poem? Yeah. I guess you're not supposed to drink salt water is the point maybe of that poem, right? But I promise this is somehow relevant, but I'm trying to remember how. I know my point. Like in the real world, if you're in the ocean, it's easy to find water. But in mathematics, sometimes there's an ocean and you can't find any water, or it's hard to pinpoint the water, right? Like if you think about the real numbers, almost every number is transcendental, but it's a little bit of work to find a number and prove it's transcendental, right? I mean, okay, maybe it's not that hard for us now, but it was hard at some point. What happened was when we got to this point, well, we actually first proved a non-constructive proof, and we just showed there exists some A that works. And then we were able to show that in some sense, the set of A that works has density 1, in the sense that if I let the size of the coefficients be in some box of size n, then the proportion of A's that work is actually 1. So it's like water in the ocean. But actually proving that you could find a specific A that works was actually kind of hard. So what happened was, this was a very surprising thing, but to find an A that works, and I won't write it down, moreover, we found an explicit A. And the point of finding this that made it kind of hard was that to prove that the A worked, it ended up being this problem of you get something like 60 linear occurrences, and you have to show that they never take the value 0. And you might have heard of Skollem's problem, which is it decidable whether a linear occurrence, integer linear occurrence, takes the value 0? It's actually an open question. For us, it was difficult because our linear occurrences it didn't have a dominant root, a unique dominant root. So otherwise it would have been easy, but because it didn't, it was kind of hard. But they all had two dominant roots. So we could use linear forms and logs, but it turns out then when you look at the literature on linear forms and logs, you have to verify that it doesn't vanish, linear occurrences don't vanish up to the first 10 to the 20 terms or something like this for the case we were considering. And I don't know how Jeff Diller did it, but he worked on a computer and somehow did that, which seems kind of surprising to me. But the point was that you could glue information mod p together, do it enough, and you get that there are no zeros. It actually grows very fast, and you can do this. So we were able to find water in the ocean. That's everything, so thank you.